Hello, I am Dr. Paris von Lockett, and today I'll be talking to you about a review of geometric symbols in SOLIDWORKS. So this is some basic CAD stuff. Hopefully you've had it in a previous class, maybe ME340, maybe eDesign 100, so it should just be a refresher. So this particular set of slides focuses on reviewing these symbols, and these relationships are important in SOLIDWORKS and also in design and with respect to this class, analysis, because they deal with the ability to make parametric designs and this concept of design intent, which we'll talk about in a little bit. We'll also related to topology optimization, which is another class that I teach, ME444, if you're interested in that, where we look at the optimization of structures and the optimization of systems. So the sketch relationships in SOLIDWORKS, you've probably seen this stuff before. On the right is a SOLIDWORKS design with a few sketch relationships shown in green. It's a circle with a given radius and then a line that has a specific relationship to a datum plane. So what we mean when we say parametric, this means that the design dimensions are driving the geometry. The geometry can be changed simply by modifying the dimensions. So as you know, if you use a smart dimension tool, we can click on any one of these dimensions, change its value, and then that particular part will change. But the question becomes, if we change the value of the dimension of one piece of our model, how does the rest of the model change? We want to make sure that the model actually changes in a way that's consistent with the use, which is that design intent piece. When we change one piece of it, does the rest of it still function as expected? The way we do that is we make relationships as much as possible and as much as makes sense between the different dimensions within our geometry. Additionally, as I said, optimization algorithms can also make use of these geometric relationships because an optimization will try and modify your part to achieve some target goal, usually in performance, but there are possibly things about the design you do not want the optimization to change, and so those will remain fixed. So here I'm showing an example of how geometric relationships can be coupled with analysis to perform what's called topology optimization. And if you're interested in this, you can click on that link in the bottom left or go try it out, Google it. This is a nice video produced by SOLIDWORKS on their topology optimization package. So on the top left, we're showing a basic part that has some constrained attachment points. Those are those circular holes. It's meant to be attached to something. And then on the top, we've got a bolt hole pattern, which means that this is actually meant for something to affix to it. So those things have to remain fixed. The sizing of the holes can't change, the location of the holes can't change, and those circles for the mounting, those can't change either. Our next step in the middle on the right, in the middle in the purple is where we perform some sort of analysis. And this is where you couple with the optimization of the FEA. What we're doing is we're trying to both remove mass, but keep the strength or the stiffness or some measure of the performance with respect to structural factors of the part the same. We're doing this, again, without changing our bolt hole patterns on the top where something's attaching to it, and those big open circles on the bottom where it's largely attaching to something. What happens if the software will do this for us? It performs many, many FEA simulations, trial and error, but guided by algorithms, and over time, it reduces the part down to what's left that you see here. And in the FEA sense, all of those rugged surfaces are just discretized elements. Hopefully you know what that means if you've done one of the past tutorials of the FEA model. And the solution then is what's left here. Supposedly has higher strength to weight ratio, meets required strength considerations. And as you can see, those points that we were not allowed to change, those are still intact. If we move over to the picture on the far right, what we see now is SOLIDWORKS sort of post-processing. It smooths the part for us. You can do this automatically, or you can go in and manually do it such that we now have something that is ready for fabrication, either direct 3D printing, injection molding, or some other fabrication process, but on this particular geometry as opposed to the rough geometry here. Once we actually have our final geometry, this also has to be analyzed to make sure that it fits within the target constraints for performance after it's been smoothed, and we can do that using, again, our FEA analysis. Once we've discretized this part, set up our boundary conditions, applied our external loads, and here's just a nice pretty picture of what the resulting stress distribution looks like in the part. All this is made possible by the coupling of this idea of the finite element analysis on this thing as a structure, along with the fact that there's some pieces of the geometry that we have to keep intact. So how do we define those pieces of the geometry that we want to either keep intact or remain in some relative type of arrangement with other pieces of our geometry? Well, we do that by applying relations. So basically, we can select items, and then we choose the appropriate relationship for those items. You're probably very familiar with this as you have selected pieces of a SolidWorks model. Different options come up for what you can actually constrain or relate with respect to those pieces. Many relationships can also be applied by simply dragging and dropping a point of one element onto the appropriate location of another element. So relationship between points or relationships on a point are probably the most basic thing that we can state within our relationships or relations in SolidWorks. So on a single point, you essentially just have the option to fix that point in space, which means it's actually not going to move. Constraints between 2 points, we can either merge them or apply a horizontal or vertical relationship to set how they're related to each other. Here on the bottom, we're showing what happens if we merge them. They collapse to the single point. Or if there's a horizontal relationship, then they're on the same horizontal plane. If we're looking to have relationships between points and lines or relationships for single lines, then a point and a line, we could make the midpoint where the point is actually sitting on the middle of the line, or coincident, so that the point actually has to be on the line, but it's free to move on the line. We can also constrain single lines, again here horizontal or vertical or fixed in space. So between a point and a line or a circle, we can also have a coincident called tangent, where the line is either tangent to the point and doesn't touch it, or tangent to the point and does touch it, as shown here. Tangent but not touching, or tangent but touching. And so these are options that we can apply for these two. We can get deeper into the relationships between two lines or two circles. Here we can define them as being parallel, perpendicular, equal, and or collinear if they are between two lines, or if it's between two circles. We have concentric, tangent, equal, and co-radial. So what do those mean? Well, we can look at specifications for each of those constraints between lines, shown on this particular page here. Our parallel means obviously they're parallels, denoted by this symbol. Perpendicular, they're perpendicular, denoted by this symbol. If they're equal, that means that they have to be an equal length, and changing one actually changes the other. Or they have to be collinear. Collinear means that they are along the same infinite line if they were extended to go past each other. And here showing examples of our our collinear relationship, our perpendicular relationship, our parallel relationship, equal length, etc. And again, hopefully you're familiar with these. You've used these in your models before. Between two circles, we can specify what those relationships mean. Concentric means, of course, that the circles are situated within one another and have the same center point. If they're equal, that means they have to have the same diameter or radius. If they're tangent, that means they meet at a single point. And if they're co-radial, then the diameter has to be equal. Essentially, that the circles will appear as one circle because they are lining up on top of each other. And finally, if we get to the point where we need to start removing constraints, and you've probably done this as well, you can select a constraint, delete its symbol, and then it'll go away. Or you can use it, the deletion method, by going through the existing relations in the property manager and delete the relationship that way as well. So lots of different things we can add, multiple ways that we can remove, And all of this allows us to specify within our design things that have to be related to each other, such that if we change one, we don't mess up the functionality of the part, or like we said, that design intent. Well, thank you for watching. Thanks for participating. Hopefully you've gotten a refresher on the symbols used for relationships, geometric relationships in SOLIDWORKS. I have an idea of how these things can tie into topology optimization, which is sort of a really cool, sort of cutting edge thing that SOLIDWORKS is trying to build into their systems, and really an optimization is moving into integrating with CAD more and more nowadays anyway. So take a look at these, review them if you need to, and as you begin to make your models, think about, in this class and even in other classes, how should pieces of that model tie together? Are there relationships that will actually make it transform better if we have to change one thing versus another, such that we don't lose that design intent? Thanks, and take care.